Okay, so now we have our linked list. And again, we got to do the same analysis, but it's going to be different because we're going to have a different backing data structure. So let's take a look at this. Remember, stacks only add and remove from one end. So since we're using a linked list, what operation do we want to avoid? Well, what we don't want to have to do is have to iterate through our linked list to find an element. So accessing an arbitrary element is big O of n, and getting to an element not near the front of the list is slow. Doing anything with an element that isn't really near the head is slow. So what do we want to take advantage of? Well, adding and removing is fast, and accessing the head node is fast. So if we can keep our operations towards the head of the list, we're going to be able to be really, 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 really fast, and that's nice. So what does this mean? The top of our stack should be near our head node, right? Our head node should be the top. And then pushing onto a stack just means adding into the front of the list, right? Adding a new node in front of the head, redirecting our head pointer, incrementing a count variable. Popping means removing the current head node, decrementing a count variable, returning the element inside the old head node. Peeking means just getting the element in the head node. These are all big O of 1 operations. The downside is you don't need contiguous memory, but linked lists do, in general, eat up more memory than an associated array. So let's take a look. Okay. We'll do the array, we'll put it on the right-hand side again, and now we'll do a linked list. Okay. So notice we now need to import our node because we're doing a linked list. And our constructor changes a little bit. Now we don't have this. Now we don't have a contiguous block. We don't have this. We don't have a dynamic array. We just have this, a head node that's none because that's an empty list, and a length is 0. So our length has come back because our nodes don't keep track of the length on their own. Okay, so let's look at push. Well, we need to create a new node, done, that contains the new element, and that points to the head node. That's what this does. Well, what do we want that node to be? We want it to be the head node. Okay, that's that. If this confuses you, think of it this way. We could do this, new head, and just self._data. I'm sorry, data head equals new head, right? This is the same, right? It's just an additional line of code. But same concept, right? Take this variable, store it here, overwrite that, okay? Just remember that when you have assignment, the assignment operator's precedent is way low, right? It's like one of the lowest precedents. So everything to the right of the equal sign gets evaluated first. And then at the very last thing that gets done is it gets assigned to this variable. So what I showed you in the multi-step process and this are the exact same statement. So we create a new node that points to the head, and we overwrite the head with that new node, and we increase our length by 1. That's all we have to do. Okay. Peek, we can come down here to peek, and we can see how that's just slightly different, right? Peek just says, hey, get the element inside the head node and return it if our length is greater than 0. Otherwise, raise an exception. That's it. Pop, we still call our peek. We still adjust our length. We still return our stored value. But now the difference is instead of nuking what is in a slot, we just move our head node, right? Remember, popping means removing the current head node and returning the element inside. Well, get the element inside, hold on to it, move the head node to the next head. I'm sorry, to the next head, to the thing after the head, right? So head.getNext, what is that? Well, that's our head node now. Decrement our length and return the element that was inside. And then our length is just our length variable, right? And every time we push, we add one. Every time we pop, we subtract one. So these are the three different implementations. Why would we choose different ones? Why, if the runtime's functionally the same, well, they're not exactly the same. Resizing an array is slow when the resize happens. So if you need all of the operations to always take the same amount of time, you need to use a linked list. If you have a lot of memory that you need to save, right? You just cannot afford to have wasted memory. But you can declare the memory at the very beginning. Okay, great. An array is going to work out well. If you're going to have lots of chunks of memory, but you're not sure how much memory you're going to need in the beginning, a dynamic array is going to work out great. If memory is not the biggest concern, but large chunks of memory is, maybe you go with a linked list. These are all the possibilities, and these are all the kind of combinations of factors that could come into play. But when it comes right down to it, all three operate the same. If you took this code that I wrote here and just substituted out array stack for linked stack or list stack, yeah, the dot_data might look different, right? Because we wouldn't have dot_data for linked, we'd have a head. But all of the calls to len, pop, and peek would all operate the same. And that's the key, right? That's the difference between the publicly visible interface and the internal implementation.